In our world today, we are faced with the critical challenge of climate change and an urgent need for clean, renewable energy sources. However, a powerful solution is emerging as quantum science intersects with solar energy technology. This convergence promises to unleash a new era where we can fully embrace the boundless energy of the sun with unprecedented efficiency. At the heart of photovoltaic technology lies an intricate interplay between light and matter, governed by the fundamental principles of quantum mechanics and electrodynamics. Photons, the fundamental particles of light, initiate a cascade of processes within solar cell materials, leading to the formation of excitons, quasi-particles that represent an excited state of the system. These excitons, once dissociated, liberate free charge carriers, generating an electrical current that powers our devices and homes. Through a multidisciplinary approach combining cutting-edge experimental techniques, advanced computational simulations, and innovative material engineering, researchers are unraveling the mysteries of exciton dynamics and charge carrier transport. This profound understanding, rooted in quantum electrodynamics, has paved the way for the development of highly efficient solar cells capable of capturing a broader spectrum of the sun's energy, maximizing the conversion of light into electricity. While solar energy holds immense promise, its intermittent nature and dependence on environmental conditions necessitate the integration of complementary energy sources and storage solutions to create a resilient and reliable power grid. This has led to the development of hybrid energy systems that seamlessly combine solar power with other renewable resources, such as wind, hydroelectric, geothermal, and advanced battery technologies. By leveraging the strengths of each individual component, these hybrid systems can provide a continuous and stable supply of electricity, mitigating the inherent variability of solar energy. The integration of quantum solar insights is driving a wave of sustainable solutions across vital frontiers. In regions affected by drought, advanced solar-powered desalination systems are providing clean drinking water, mitigating the global water scarcity crisis. Electrolysis chambers, powered by highly efficient photovoltaic systems, are splitting water into hydrogen and oxygen, enabling the generation of clean, renewable hydrogen fuel for a wide range of applications. Moreover, industrial plants are transitioning towards sustainable practices, utilizing solar-driven manufacturing processes and solar thermal systems, reducing our reliance on fossil fuels and mitigating the carbon footprint of various sectors. Additionally, researchers are exploring ways to utilize solar-derived energy to power carbon capture processes, allowing the captured carbon dioxide to be converted into value-added products, such as fuels, chemicals, or building materials, effectively promoting a circular economy. This transition towards a sustainable energy future driven by quantum solar insights extends beyond mere technological advancements. It necessitates a holistic approach that encompasses environmental stewardship, economic viability, and societal engagement. By embracing a circular economy model, where materials are responsibly sourced, utilized, and recycled, we can minimize the environmental impact of these systems throughout their life cycle. Furthermore, fostering public awareness and active community participation is crucial to ensuring the successful deployment and acceptance of these innovative solutions. In conclusion, the convergence of quantum-level solar energy research and the development of innovative sustainable solutions represents a transformative opportunity to shape a responsible and resilient future. By applying the profound insights gleaned from the investigation of exciton dynamics and electrodynamics, and seamlessly integrating solar power with complementary technologies and hybrid systems, we can create robust and efficient systems that address pressing global challenges, from water scarcity to energy security and environmental preservation. However, this endeavor requires a holistic approach that prioritizes environmental stewardship, economic viability, and societal engagement, ensuring that the benefits of these innovative solutions are shared equitably and responsibly among all.